Hello, today we're going to talk about what's called the normal contact force, okay, which is a force that you're feeling right now, unless you're in space, okay, what it is and how it works. And what we're doing today really is moving from the horizontal plane, which is what you've been working in so far. So you've done suvat, sort of left and right on flat ground, and you've done F equals ma using forces to calculate the acceleration, but again on flat ground only going left and right, cars, trains, planes, bikes, that sort of thing. When we talk about normal contact force, we're talking about forces and acceleration in the vertical direction. Okay, so a bit of notes to take. So if you sort of draw this and make a few notes as we go along, pause the video if you need to. Okay, so there's a picture of a book sitting on a table, and to calculate the weight of an object, you do its mass times the gravitational acceleration, F equals ma. Okay, so mg. If the book was 5 kilograms, 5 times 9.8, 49, so that weight is 49 newtons. But if that's the only force, then the book should be accelerating downwards. Okay, because an object will accelerate in the direction where the force is greatest, and there's only one force acting downwards, so why isn't it accelerating downwards? Well, very simply, it's because there's another force acting upwards. Okay, equal and opposite forces. Okay, and since the book is in equilibrium, it's not accelerating, it's not decelerating, it's just sitting there, a constant velocity of 0. That opposite force acting upwards must be equal to the weight, and we call it R for reaction, but that is down there what's called the normal contact force. Okay, normal contact force. And the reason I say you're feeling it now is because if you're sitting down, then the chair is putting the normal contact force back into your bum, equal to your weight. Okay, if you're standing up, then the floor is giving a normal contact force into your feet. Okay, and if you're standing still, so you haven't jumped or anything like that, if you're just standing normally, then the normal contact force pushing upwards is equal to your weight. Okay, your mg, mass times gravity. All right, so that's if things are just sort of sitting still with nothing else going on. Obviously, if you put like a heavy bag on your back, your weight increases, but you still don't fall through the floor, so that must mean that R increases. And it's actually R that you feel. You don't feel your own weight. Your own weight has no effect on you. It's the contact force that you feel. It's the pushing back force. Okay? If you were in space where there's no gravity, you'd feel no contact force, okay, because mg would be 0, so R would be 0. You'd feel nothing, okay. It also goes a long way to explaining the strange sensation you get in lifts or roller coasters when you are accelerating quickly upwards and downwards in the vertical direction, okay. We don't often accelerate in the vertical direction very much, do we? Only sort of going up and down stairs or going up and down in a lift. Most of what we do as humans is side to side. Okay. So a little bit more notes then, just saying that force acting upwards, R, is the normal contact force. Okay, and really important at the bottom there is that it always acts perpendicular to the surface. Okay, so at 90 degrees to the surface, that means. All right, so when you've got flat tables, because the table is horizontal, it means that mg is acting downwards and R is acting upwards. It gets a little bit more complicated, okay, when you go onto a slope, which I'll show you in a second. So there's a flat surface, doesn't matter what the object is, R always acts upwards. But when you go onto a sloped inclined plane, we call it, and you don't need to do these in M1, but I thought I'd just show you, even though mg still acts downwards, because that's the direction of gravity, R acts perpendicular to the slope. Okay, and it gets a bit complicated then to do the maths, which is why you don't do it in the first year of mechanics. You'll do it next year, looking at sloping planes. Alright, but R always acts perpendicular to the surface, even if the weight is acting downwards and we're on a slope. Okay, so let's have a look at some questions then. So the first one that I've got here is very straightforward. We've got a brick of mass 1.2 kilograms and it's just resting on a platform, a plane. Okay, so you'll need diagrams for these. Anytime you've got forces needs a diagram. So here's my brick. It's got a mass of 1.2 kilograms. So first job is to mark on its weight. Okay, so acting downwards, 1.2 times 9.8 is 11.76 newtons. So 11.76 newtons acting downwards. Okay, it's resting, so its acceleration is 0. Acceleration is a double arrow, remember? Okay, I mean its velocity is 0 as well, but it's acceleration that's most important here. Because its acceleration is 0, we're in equilibrium. That tells me that the contact force upwards must be equal to the weight. Sorry, that was my daughter coming in to speak to me. So, the contact force upwards must be 11.76 newtons as well. Very, very simple, equal to the weight. If we have a look at another question, this is quite a lot more difficult actually. So, a man of mass 80 kilograms stands in a lift. Find the magnitude of the normal contact force when the lift is stationary, when the lift is accelerating upwards at 0.5 meters per second squared, and when the lift is accelerating downwards at 0.8 meters per second squared. Draw a diagram for each part. Okay. What I'm going to do first is work out mg. So that's 80 times 9.8. 9.8 in maths. I know it's 9.81 elsewhere, but we use 9.8. That's 784 newtons. Okay. So when the platform is stationary, the lift is stationary. Oops. So here's our man. There we go. And his weight is pushing downwards 784 newtons. And because the lift is stationary, it's not accelerating, he's in equilibrium. So I'll put 0 there. Just like the brick on the first question, the normal contact force R must be equal to 784 newtons. So that's easy enough. Okay, that's the force that this man is very used to feeling, because every time he's standing still, R is equal to his weight. Okay, different when you jump and come back down because you've got to decelerate. Now let's have a look at part B. So if I copy and paste my man, look, easiest thing. Okay, so let's have a look. What's the same, what's different? His weight is the same, he's still the same man. So that's unchanged. But this time the lift is accelerating upwards at 0.5 meters per second squared. What does that tell us about the forces? Well, they're not equal anymore. Okay? Because if they were equal, he wouldn't be accelerating. He's accelerating upwards, which tells me that the forces acting upwards on this man are greater than the forces acting downwards, and that's why he's accelerating up. So R is now bigger than 784. How much bigger? Well, we'll have to use F equals ma to find out. So, if we take up as positive, because that's the direction that he's moving or accelerating, so R is positive, 784 is acting down, so that's negative. That's both of the forces, and that equals ma, so 80 times 0.5. So R minus 784 is equal to 40. If we bring the 784 over to the other side, 784 plus 40, whoops, is 824. So the reaction force is 824 newtons. Okay, Now, if you want to work that out as an equivalent sort of mass, that's equivalent to his mass increasing to 84 kilograms. Okay, if he was an 84 kilogram man to start with, he would always feel a reaction force of 824 newtons. So that's why when you get in a lift and the lift starts to move, starts to accelerate, you sort of feel a bit of extra weight in your knees, and your knees might bend slightly. It's the equivalent of temporarily sort of almost becoming heavier. Okay, you're not becoming heavier, but what you're feeling is a much bigger contact force, normal contact force, than what you are used to. Okay, this man is used to feeling a contact force of 784 newtons, and all of a sudden he's feeling 824. That extra 40 newtons makes his knees bend a little bit because you're not expecting it when the lift first starts moving. Okay, so that explains why you feel sort of that little strange feeling in your knees when a lift starts to move upwards. Okay, let's have a look at what happens when the lift is on the top floor and going down this time. So, again, his weight is unchanged, and this time we're accelerating down at 0.8 meters per second squared. Okay. Right, if we're accelerating down, that should tell you that forces acting down are greater than the forces acting up, and so R this time is smaller than 784. Remember what I said before about small arrows for smaller forces? So R must be less, and that's why it's accelerating down. And again, now, what I'm going to do, I'm going to take the direction of acceleration to be positive every time. So it's different to the one before. So in part B, we said up was positive. In part C, we're going to say down is positive. It just makes the maths a little bit easier with less negatives. So this time, 784 is the positive force because it's acting down. R is the negative force because it's acting up, opposite to the acceleration. And again, that equals 80 times 0.5 because F equals ma. So 784 minus R equals 40. Now, to rearrange that, you'd need to move R to the other side, make it positive, 40 to over there, and it goes negative. And what you end up with is 744 equals R. R equals 744 newtons. And if I do 744 divided by 9.8, that's a little bit like the man dropping to a mass of about 76 kilograms. Okay, so you feel lighter when a lift accelerates downwards. You're not lighter, your weight is the same. What's different is the contact force that you're feeling upwards on your feet. Okay, and because that's less, that's the contact force that somebody who's 76 kilograms feels all the time. But if you're used to being 80 kilograms and having a contact force of 784, it feels very different. Okay, so you'll never stand in a lift the same way again now. Whenever I get in the lift, all I can think about is contact force, acceleration and deceleration, because I'm a massive nerd. Okay, but if you look on a lift, on the information panel, it quite often tells you the acceleration rate. So if you do a quick bit of mental maths, you could work out your contact force while you're going up and down, if you're a massive nerd like me. Okay, so those are fairly typical questions for working out normal contact force. It's easy to do when the thing's moving because it's equal to your weight, but then if you start accelerating up or accelerating down, R gets bigger or R is smaller than the weight, even though the weight doesn't change. Okay, have a look at this question then. So there you go, a little sentence start with saying it's not always equal to the weight. Right, imagine one of those giant metal shipping containers, okay, and I've said it's 3 tons, 3,000 kilograms, and if you times by 9.8, that's 29,400 newtons, okay, and it's currently sitting on the dock, and they've put some cables on it, and they're going to lift it up onto the ship. So, while it's just sitting on the floor, and it's got cables attached, but those cables are slack, wiggly, okay, they're not doing any work at the minute because they've only just been attached. We've got a weight of 29,400 and the normal contact force, the floor is doing all of the work, also 29,400. Okay, Then what happens then, the crane starts to sort of tighten up the cable. They call it taking a strain. And we'll look at what happens when the cable is tight, but it's not tight enough to start lifting the container. So we've still got 29,400 newtons acting downwards. We've got the cable doing 10,000 newtons of lifting. Okay, but the container is not moving. It's not moving because 10,000 newtons is not enough to lift something that's got a weight of 29,400 newtons. Okay, if anything, this container should be accelerating downwards, but it's not, because there's still a normal contact force. But remember, we're in equilibrium. This container is not moving anywhere, it's just sitting on the dock, even though the cable is doing some lifting. Okay, if you imagine you've got a rope and you're trying to lift something heavy, you can try really hard, you can do a lot of effort, you can put a lot of force into the rope, but if you're not doing enough force, the object is not going to lift. And that's what's happening here. Even though the cable is doing some lifting, it's not enough. But I only need 19,400 newtons, because 10,000 and 19,400 is equal to 29,400. So the work now is being done between the cable and the floor. Okay. If you're unlucky enough to be underneath it, it's not as heavy, it's not pushing down on you as much as it was. Now let's look what happens when the container is about to be lifted off the floor. So still got a weight of 29,400, and the cable now has gone so tight that it too has got a tension. Okay, call it tension when it's a cable. 29,400. So what is the container doing? Is it accelerating at this moment in time? No. Okay, and it's not accelerating because it's in equilibrium. Okay, is there a normal contact force? No, it doesn't need to be, because the tension is doing all of the work. Look, okay, R wouldn't push up any more than weight. I mean, while it's just sitting on the dock, why would it be bigger than the weight of the object? Okay, so it's still on the floor, still touching the floor, but there's no R. Which means if you walked over to this container now, you could actually slide it along the floor at this point in time, quite easily. Okay, because if there's no R, there's no friction. So you could push this container around now like it didn't weigh anything. Because even though it's in contact with the ground, there's no contact force required. The work is being done by the cables, but really importantly, it's not actually lifting off the ground yet. As soon as you increase that tension to more than 29,400, then it will lift off the ground, because then the force upwards will be bigger than the force downwards, and you can use F equals ma and it will accelerate upwards. Okay, obviously then as you lift it up, you put it back down, the whole thing goes in reverse. Alright, so as you put it on the ship, to start with, the ship feels no weight because R is 0, but then as the cables sort of start to loosen, more and more of the weight gets transferred to the ship, until eventually you take the cables off and the ship is doing all of the R. Okay, pushing back upwards. And you can even draw a graph of it then, look. So that's what happens. Initially when the cables start to tighten up, I mean they're tightening up but they're not doing any work, so the normal contact force is equal to the weight. And then you have this transfer then, where like at this point maybe, the tension is doing 20,000 newtons of work and the floor is only doing 9,400 newtons. Okay, and then but down here you've got maybe the cable is doing 28,000 and this is only doing 1,400 newtons of work. Until you get to here, this is where the cable is doing all of the work and the tension in the cable is equal to the weight of the container. Okay, so just things to be aware of, that normally if things are sitting on a surface, the normal contact force is equal to the weight. If you start to accelerate up or accelerate down, then R will no longer be equal to the weight. And if you've got a cable involved or some sort of lifting going on, or even something pushing down on it, that can increase. Okay, so think of a situation where somebody's trying to push a box. Oops, let's try that. That's rubbish, isn't it? So you've got a box and it's got, let's just say it's got a weight of 800 newtons. Okay, if they put their arms on and push down at an angle like that, which if you think about it is probably what you do most of the time, you're actually pushing down on the box. A little bit of your force is pushing down. So by putting an extra force down, what you're doing is forcing R to be bigger. So if you're adding an extra 50 newtons by pushing down on the box, this is now 850 newtons. Okay? You don't have to fully understand this, but what happens is when you increase R, you actually increase the friction, and so you're making it harder to push the box by doing that. Okay? What you'd be better off doing is pushing horizontally, because then your force has no effect on R. So let's go back to being 800. Okay. Or if you want to make life really easy for yourself, what would be easier is if you tied a bit of string on it and did that, because now you're lifting the box a little bit. Look, there's a little bit of force lifting, and so maybe you could get that down to 750, which will reduce the friction, okay, and make it easier for you to pull the box. Okay, so R is not always equal to weight. It depends on other forces, it depends on acceleration. Okay, but R always acts perpendicular to the surface, and use F equals ma to calculate if you've got acceleration going on.